An unknown radioactive element decays from 80 milligrams to 48 milligrams after 3 months. We want to find the exponential decay model for the decay after t months. Then we want to know when will a sample of 80 milligrams decay to 5 milligrams. So to model this situation, we'll be using the exponential growth and decay function p of t equals p sub 0 times e raised to the power of kt, where p sub 0 is the initial amount or starting amount, k is the exponential decay rate, and since we have decay, k should be negative, t will be the time in months, and p of t will be the amount of radioactive element after t days. So let's find the exponential decay model on the next slide. Reading this question again, we're starting with 80 milligrams of radioactive material, which means p sub 0 is equal to 80, or 80 milligrams. And then after 3 months, we have 48 milligrams of radioactive material. So after 3 months, or when t is equal to 3, the amount of radioactive material, or p of t, is equal to 48. Now we can sub these values into our exponential decay function and solve for k, the exponential decay rate. So we want to solve the equation 48 equals 80 times e raised to the power of k times t, but t is 3, so we have e raised to the power of 3k. And now to solve this, we want to isolate the exponential part. So we want to divide both sides by 80. This simplifies to 1, and 48 divided by 80 is equal to 0.6. So we have 0.6 equals e raised to the power of 3k. And now we want to take the natural log of both sides of the equation so that we can apply the power property to the logarithm on the right. We can move this 3k to the front. So now we have the equation natural log 0.6 equals 3k times natural log e. But natural log e is equal to 1. Remember, natural log is log base e. And since e to the first power is equal to e, this is equal to 1. And multiplying by 1 doesn't change anything, so a lot of times you'll see textbooks not even write this. So to solve for k, we just need to divide both sides by 3. And now we'll get a decimal approximation for our exponential decay rate. So we'll have natural log 0.6 divided by 3. We do want to include quite a few decimal places for accuracy, so let's include 6 decimal places. So we're going to have a k value of negative 0.170275. And now we have the information we need to write our exponential function. We know that p of t is going to be equal to the initial amount of 80 milligrams times e raised to the power of negative 0.170275 t, where t would be the time in months. So with this function, if we knew the number of months that had passed, or t, we could determine how much of radioactive material would be left. But for the last question, we want to know when will a sample of 80 milligrams decay to 5 milligrams. So they're telling us that we want p of t to equal 5 milligrams. We want to know t, or how long this would take. So now we want to solve the equation 5 equals 80 times e to the power of negative 0.170275 t. Now this is very similar to the last equation that we solved. So we'll start by dividing both sides by 80. 5 divided by 80 is equal to 0.0625. Just as before, now we'll take the natural log of both sides of the equation and then apply the power property of logarithms here, so we can move this to the front. So we'll have negative 0.170275 t, again, times natural log e, but natural log e is equal to 1, so we'll leave that off. And now to solve for t, we'll divide by this coefficient. This simplifies to t, and now we'll get a decimal approximation for t. If we round this to the nearest tenth, we can say that t is approximately 16.3 months. Just be sure you round to the correct place value based upon the question that you're asked. Okay, that's going to do it for this example. I hope you found this helpful.